In this video, I want to discuss different ways of thinking about solutions to systems of linear equations. And the traditional way, well, maybe not the traditional way, but usually the first way that we're used to is a picture where you graph the equations. So for instance, if you had, here's the old picture. Well, before I do that, maybe I'll just give the example. Let's say we wanted to solve x plus y equals 3, x minus y equals 5. The old picture is to graph x plus y equals 3 and x minus y equals 5 and see where they intersect. First of all, it's easy to figure out what x and y are. We get, if you add the two equations, you get 2x is 8, so x is 4, and then when you plug in 4, you get y equals -1. And the picture is, if you graph x plus y equals 3, then this is y equals -x plus 3. So it's a line with slope -1 and y-intercept 3, like that. And then the other one is the same as y equals x minus 5. So that's with slope 1, and the y-intercept is -5. So you have something like this. And where they intersect, the solution for -1 is where these two lines intersect. That's the point of intersection. This is the old picture. Maybe I shouldn't say the old picture, but it's the picture that we're used to. Now, when you take a class in linear algebra, you learn a different picture. And where this different picture comes from is from the augmented matrix. If you write the augmented matrix of this system, it's this. I'm writing the line. Technically, the line is not part of the matrix, right? I mean, the matrix is actually this, but I usually write the line just to indicate that we have a system of linear equations. The new picture is going to come from the columns of this matrix. And the idea is that we can think of solving x plus y equals 3, x minus y is, equals 5, as taking this matrix times the vector xy equals 3, 5. And this matrix times a vector here can be rewritten like this. X times 1, 1 plus y times 1, -1 equals 3, 5. So this is the new way of thinking. The new way of interpreting what it means to solve the system of equations. And you see that these two columns show up. These were the columns of the matrix. The columns of the coefficient matrix. And now we're asking, how many of 1, 1 and how many of 1, -1 do you need to get 3, 5? So now the new picture is this. I'm about to draw the new picture. You have the vector 1, 1. I'll do it in blue. Here's 1, 1. And you have the vector 1, -1. I'll do it in green. Here's 1, 1. and here is 1, -1. The question is, how many of the blue and green vector do I need to produce the desired vector 3, 5? So what we're trying to produce is the vector 3, 5, which is maybe here. Oh, I should do a different color. Like that. And to say that x is 4, what was the answer? 4, -1. To say that x is 4 and that y is -1 means that I need 4 of 1, 1 So if I take 4 of 1, 1, I'm going to get 4, 4, which is, say, here. Do it like this. And then I need to add -1 of 1, -1. So if I do -1 of 1, -1, I get -1, 1. And if I add that vector to 4, 4, I'll get 3, 5. 3, 5 is 4 times 1, 1 plus -1 times 1, -1. So this is the new picture of a system of equations. I have the columns. See, the columns now play the role. That's one of the benefits of rewriting the system using matrices. It's not just that we have a shorthand that you don't have to write down the coefficients or the variables. I mean that's one advantage of the matrix, that you don't have to write down the variables. But the main advantage, I would say, is that you have columns to work with. And these columns give you a new way of thinking about what it means to solve a system of linear equations. It's what combination of the columns do I need to produce the output? The output is the vector. The output is the vector here. And it's good to keep both pictures in mind, but when it comes to understanding span and linear independence, you want to keep this picture in mind and think about solving systems of equations using this picture, not the other picture. Okay, thanks.